Hi everyone, welcome to today's webinar. Today's webinar is called Technical Answers to Common Questions, and we are covering ground testing theory and application. I am Meredith Kenton, Megger's Digital Marketing Specialist. If you have any questions about webinars in general, not technical questions, feel free to reach out to me via email. If you have questions during today's presentation, I ask that you submit them on the panel on the right-hand side of your screen. We probably won't have time to get to questions at the end, but Jeff will get you a response via email in the days following this presentation. And on that note, I would like to introduce you to Jeff Jowett, our Senior Applications Engineer and ground testing expert. Jeff, you can say hi.
Good morning, everyone. I thank you very much for taking time out of your schedules to attend our webinar.
Awesome. And so today's webinar is a little different. If you've been to some of our webinars in the past, we split it up into two sections: ground testing theory and then ground testing application. And I will be asking Jeff questions and he's going to answer it for you guys. So let's get started. What does the term ground mean, Jeff?
Okay, this may seem like a no-brainer up front, but actually it really isn't. And I want to make a comment about this will apply pretty much generically throughout the presentation. Those of you who are working alone, you have it much easier because there's a lot of flexibility that you can just go with the flow as far as your own activities. But those of you who work with any kind of third party, if you have an inspector involved, an insurance guy involved, a client involved, anything of that sort, just make sure you're always on the same page. And this is a good place to start because ground means quite a few different things in different parts of the application or the industry. So what we're typically referring to as a ground with respect to ground testing and so forth is what we show here, a metallic contact with the surrounding earth, typically a ground rod, but this could be a whole substation grid. They're fundamentally the same thing, putting metal in the ground so you have a good low resistance contact with the soil so that currents that you don't want in your electrical system, that would be mostly things like lightning strokes and fault currents from the utility and from other sources. You want to get them into the ground and out of your electrical system so they're not doing damage and not causing a hazard to personnel who happen to, put their hand on something metal and get shocked, and we don't want that. So that's fundamentally, it's a ground electrode, and that's fundamentally what we're going to be going back to again and again throughout this presentation. But the term is also used in a number of different ways. And a lot of times when someone says a ground, they're actually referring to the ground conductor, which, will be running throughout your building. And they may be simply referring to making a contact or an attachment to that conductor. And also, a lot of times they're referring to a ground fault. So someone will say, well, I saw a ground in the motor. Well, what they mean is that the insulation broke down and there was an electrical contact into the grounding system, and they refer to that as a ground. So just, if you're working on your own, you're fine. But if you have third parties involved, make sure that you're both talking the same language because it can cause a lot of confusion that then has to be sorted out later, further down the line.
Awesome. Okay. Next question. How does a ground tester perform its test?
Okay, let's see. Fundamentally, we have a slide that goes along with this one, and this is fundamentally telling you is it's basic Ohm's law. There's no curveballs or anything like that in ground testing. It pretty much operates by injecting a current into the soil, which acts as the fundamental current that the tester is going to make its measurement from, and then the tester looks at voltage drop caused by the resistance of the soil, and it knows those two parameters, and now it calculates out a resistance reading. So you'll see a resistance in ohms on your display. That's the resistance of the soil to the point where you placed your potential probe, and we're going to come back to that a little bit. And the fourth element here, power, does not really figure much directly, at least in a ground test. Ground testers are very little power, which keeps them safe as far as the operator is concerned. They use very little voltage and very low current, just enough to make a measurement. So there's not a whole lot of power factor involved in this, but it's pretty much straight Ohm's law. Okay.
Awesome. All right, Jeff, why should I bother to test the ground?
And I think we have a telltale, yes, we do. And this is pretty much the reason. We see some consequences of ground faults here, possibly utility ground faults, and certainly in the case of the cactus over there, that would be lightning, and the tree as well. These are catastrophic problems that occur on your electrical system, and you want to get them out of your electrical system before they damage equipment or injure a person. And so the problem with grounding electrodes is they corrode away by the natural effects of the soil around them. They can corrode away. One of the grounding materials companies a few years ago, and this was Linkol XIT, you can probably find this up on their website. They actually did a study of installed grounds, and they determined that as little as 2 years, they started to see substantial corrosion in the worst of environments. That varies a lot with the environment that you're in, but certainly some environments are highly conductive, and so you can lose your grounding electrode, and you don't see it. It's buried out of sight. You see the wire going down into the ground, and you think everything is fine, but it's not. And so fundamentally, that's the answer to your question. Why should I test the ground? Because it may no longer be there. And if you have a fault condition, then you don't have the protection that you should.
All right. And what do I do if my ground is bad?
There is fundamentally the most common applications to a situation where you've run a ground test and you've gotten 52 ohms. Well, that's unacceptable in any situation. You got to do something about that. So the most common way is to either drive a deeper rod. So we see a picture of a rod here. You can put a coupler on top of that and then another rod, and use some sort of a hammering device and drive it into the ground. That's one way. And then the other most common way is to add more rods in parallel. And so the difference here is probably, in general, the really best method is the deep driven rod. Of course, you get a room full of experts and they'll argue this for hours. So it's not cut in stone. But I would say overall, probably the best method is the deep driven rod, especially if you can get down to water table, because that gives you really good protection. The problem with it is it's expensive, and the deeper you have to go, obviously, it gets worse and worse. You hit bedrock and things like that. So it's a good solution, but it is expensive. If you add parallel rods, that's a little less difficult. In fact, in some situations, it can be relatively easy. Just space them farther away than they are deep, because if you have them too close together, it doesn't do any damage, but it's just they start to act as a single rod rather than in supplements to your grounding system. So you kind of defeat the purpose if you're adding them too close together. And then the third alternative, which we kind of depict here, again, if you go to your grounding materials companies, they can help you with this. They have all of these types of systems available. There are a number of ground enhancement systems that you can employ. This particular one shows a trench around the ground rod, which in turn a conductive material would be installed in that trench, which would promote the flow of current away from the ground rod and, back where it came from, the utility or wherever. So that could be a whole webinar in its own right. So we're only going to touch on it here. But if you're interested in these methods, try your grounding materials companies, and they will most certainly be able to help you with these. If you're in particularly difficult situations, which would be maybe like the desert or something like that, then you could go to these more extreme measures to improve your ground.
All right. Next up, what is the difference between resistance and resistivity?
Okay, another fundamental question that looks like a no-brainer, but it's not. You really, again, especially if you're dealing with any third parties, want to make sure that you're talking the same language, and you want to know that there's a critical difference between resistance and resistivity, although they sound so similar. Resistance is your installed grounding electrode and its relationship to the surrounding earth. The resistance between the electrode and what is referred to in the literature is remote earth. You hear that term. It just means the distance at which the current has dissipated to the point where it is no longer a problem. Resistivity, on the other hand, is the characteristic of the soil itself. This would be the reciprocal of the conductivity, in other words, of the soil itself. It's a property associated with the composition of the soil. And it can be very good and it can be very bad, and it depends on where you are. If you're in Florida, sandy soil, you can have a real problem with high resistivity. Same thing with out in the desert. If you're in rocky areas like foothills. Other areas where you got mostly loam soil, you've got very low resistivity and you're in a pretty good grounding situation. But this shows the fundamental test for resistivity, which would be this is kind of like what they call the Wenner method, where you have 4 terminals and your outside current terminals inject a test current, and then your inside potential terminals determine the voltage drop, and up on the display you see the resistance between those 2 potential terminals, and then you apply that to, let's say, the Wenner method, 2 pi AR, and that gives you a resistivity measurement. And there's a lot that you can do with that. Okay.
Awesome. And what is fall of potential?
Fall of potential is the fundamental means of testing a ground, and we have sort of an outline of it here. It's not the only way to test the ground, but it's the most fundamental one. It's the most reliable. It's where you hook onto your ground rod with the ground tester, and then you have a current probe at a remote point out in the soil, hopefully as far away as you can get it. And that's going to put a square wave test signal from that current probe back to your test ground. And then the tester's going to use that current signal to make its measurement. And then you're going to take your potential terminal, and this doesn't represent, a dozen different rods. What it represents is one rod, but moved to a number of locations, a selected distance apart. So they might be 10 feet apart or 15 feet. The operator pretty much decides that for himself. But you take these series of measurements and then you graph them, distance versus the resistance at those different points. And that graph then tells you whether you made a good measurement or not, and it tells you what the measurement is. And that's what is called fall of potential. And that's the most fundamental way of doing a ground test. It's in the IEEE standard 81 defines it. And there are other methods which are devised to generally for 2 purposes, either to save time because this is fairly labor intensive. So you have methods that save time, and then you have other methods for difficult situations. And these are all available in the general literature, and we're going to provide you at the end of this webinar, we're going to provide you with a handbook that describes all of them. And then, of course, you're welcome to talk to me about them at any time.
Yes, and one more thing about the fall potential. We just recorded a fall potential video tutorial just to go along with this webinar. It's about 10 minutes long, so you will get the link to that video after this. It should come from an email directly from GoToWebinar with a copy of the recording as well. So be on the lookout for that.
Okay.
Right. And why do I need to perform a test in accordance with a method?
Okay, very fundamental question. Most operatives in various types of electrical testing are used to generally, you know, in most situations, you hook up two leads and you take a measurement and that's it. So if you were measuring voltage or something, that's pretty much how it works. The problem with ground testing is most electrical testing is done on a discrete item, a motor, a circuit, whatever, so you know what it is. With a ground test, you're connected to the entire planet. And so that introduces a variable that you don't have in most electrical testing, and you have to deal with it. So if you just ran leads out, and you know, this is fairly commonly done, and it's a little bit risky. If you just ran leads out and put probes in the soil and took a measurement, yeah, you might get a good measurement. You might be lucky. You might be at the right point, and that measurement might be perfectly good, but you don't know that. And if you're dealing with a client, you're not going to be able to get away with that. So the test method is an industry prescribed procedure for assuring that your measurement is, in the extreme case, completely accurate, or in some cases, for this save time or whatever, you may use a method that's a little bit briefer, and there may be a little bit of inaccuracy introduced into the result as a result of that. But nevertheless, you know that you have a reasonably reliable or a thoroughly reliable answer depending on the method that you used. But that's the reason that you follow a test method. It's fundamentally to deal with the uncertainty of the fact that you're connected, an electrical connection, to the entire planet.
Awesome. Okay, now we're moving on to part 2, ground testing applications. So Jeff, the first question I have for you is, can I use an insulation tester to do the same test?
Okay, absolutely not. But it does happen a lot. Fortunately, I don't get as many calls as I used to. That used to be a fairly common call, especially with operators who are dealing with like a central stores that somebody deals out to them in the morning what equipment they're going to use on that particular job. And in the old days, the insulation testers and the ground testers used to look so similar that it was very common for guys to get out to the job and find that they have an insulation tester instead of a ground tester. And unfortunately, I had to tell them, well, you wasted 25 minutes driving out there. You're going to have to go back again and get a different tester. Nowadays, the appearance of them are starting to diverge somewhat. So I don't get that call as much as I used to, but it's still a potential hazard. So no, the issue here is a ground tester works with low voltage and low resistance. It's on the low end of the resistance scale, whereas an insulation tester wants to measure all the way up on the extreme high end of the resistance scale, because you don't want your insulation to be low resistance. Obviously, you want it up in the megohm range at least. And so you have a tester that puts out a lot of voltage, sees very little current, and gives you a very high resistance reading, whereas your ground tester is on the other end of the scale. And so, no, they are not interchangeable. And if unfortunately you did get to a job with an insulation tester, you have no alternative but to go back and get a different piece of equipment.
All right. The required measurement is of resistance. Why can't I just use a digital multimeter?
Again, a fairly common function. It seems to make sense. You're measuring resistance. Your multimeter, your DMM, has a resistance function on it. And so you'll just hook it up and take a measurement. The problem with it is a couple problems with it. It's 2 leads. And so to do, like we already mentioned with respect to a fault of potential test, you need 3 leads to do that. If you do a multimeter with 2 leads, you can hook up to some sort of a return, like a fence line or the water pipe system, and it will give you a measurement. But there's too much guesswork involved in there. For one thing, the DMM typically that's DC, and there's a lot of noise in the soil. All these computer rooms and offices and things like that, they're chopping up the sine wave, and they're using what they need to run their computers, narrow voltage DC, and they're putting the rest of that back on the grounding system. A lot of that is with the parallel grounded neutral. A lot of that's getting back into the soil, and it's got to go back where it came from, the transformer that is feeding your site. And so that's going to get into your measurement with a DMM. And so, no, the uncertainty with a DMM is really huge. You might get lucky, but that's the best you can hope to do. So, no, just abandon that idea. Don't do that. Get a ground tester, and you can prove that you have an accurate measurement.
Awesome. Okay, what is the difference, Jeff, between a 2-point, a 3-point, and a 4-point test?
Okay, 2-point, we just kind of discussed that briefly. That is actually in the literature, and it is legitimate as a drop dead type of test where you have no other alternative, which generally would be you're testing a building in downtown Manhattan, let's say. So a 2-point test, also called the dead earth test, it's called that because it uses a return, which is not part of the electrical system, so it's electrically dead. The water pipe system is generally what is used, although sometime it could be, building steel or something like that. And it's where you have one lead going to the ground that you're testing, and the other lead is going to something like the water pipe system, which you hope contributes very little to your measurement. And you take a reading, and you're getting a loop resistance of the whole thing, but you're hoping that most of that is just your test ground. And so that's your 2-point or dead earth method. You can use it, but it's a drop dead method for situations where you can't do anything else. Now, the 3-point is, of course, what we've already described. That's your really good, reliable test where you've put a current probe out there and you set up a test current and you've moved the potential probe and you plotted your resistance readings and you've gotten a perfectly good test. And then finally, your 4-point, you can do a 4-point ground test. It's just a little bit more accurate. It's not really necessary. But where it is necessary is soil resistivity. So if you're going to do soil resistivity, you must have a 4-terminal tester. And the main thing to think about here is when you're making a purchase, just use your crystal ball, look into your testing future a little bit. And so don't buy, 3 terminals are obviously less expensive. You're buying 3 instead of 4. And so it's sort of an automatic response, you might think, to buy a 3-terminal tester. But then maybe 6 months from now, especially if you're a testing service or somebody like that, you're going to get a proposal for a job where you need soil resistivity, and uh-oh, I can't do it. I don't have the tester for it. So just look into your crystal ball, and if you think you may get that type of job, then make sure that you're prepared by having a 4-terminal tester.
Okay. And can't I simply just make a measurement to a reference ground?
Yes, you can. And that's what we just described as the dead earth method. This, let me mention that this is actually described in the IEEE 81. So if you're dealing with a third party and you don't have any other method, you're down at Times Square and you need to make a method, you need to make a test. You can do a 2-terminal only if no other possibility exists. And this is fundamentally what a 2-terminal test looks like. And so it is described in IEEE 81, and the limitations of it are listed there. So it would be a good idea to, if you're dealing with a third party, it would be a good idea to know what those limitations are so that you can then discuss it, in an informed manner, and the third party will accept your test result. So fundamentally, that's where you use your 2-terminal method, but don't use it unless no other alternative exists.
Okay. How do I know if my ground is good?
And in that case, we've talked about running a test. So let's say you've done a test and now you're stuck with the result. And this is a fairly common question. I get called at the office on this quite frequently. Okay, you've done a test and you've done a perfectly good test and you got a number. So now how do I interpret that number? Okay, in the literature, you will see all the time 25 ohms or less. That comes from the National Electric Code. It is very forgiving. The National Electric Code is concerned with safety. It doesn't want people being shocked, and it doesn't want buildings catching fire. It does not care whether your computers are running to maximum efficiency or your computer-controlled production line is running at maximum efficiency. And you look at the preface to the NEC, it actually says that in there. I'm not just extemporizing on this or anything. It's actually in there. So that's for safety. And so the 25 ohms is a fairly forgiving standard. If you meet that, you meet code. Okay, you're good, you're safe. But that does not guarantee that your computers aren't going to see noise. You're not going to get pixelation somewhere in a computer-controlled system. So for those standards, you want to have a much lower ground resistance. And industry standard for commercial and industrial is pretty much 5 ohms. So generally, if you can get under 5 ohms, you're good by most standards. And then there are some others that are more demanding. So, industries like nuclear, for instance, they'll set up their own standard and they'll tell you, we want to see this. A lot of companies set up their own, very large companies or telecom, for instance, that are across the whole country. They'll have their own standard. So just consult them and they'll tell you, okay, we want to see a 2 ohm ground, or we want to see a 1 ohm ground, or whatever. And then for things like generation, the utilities, substations and things like that, they typically want to see much lower resistances. And very often you'll run into a 1 ohm ground for something like a substation. But that will be imposed by the authority that you're working with. And so you just determine that and then go ahead with your testing, and you want to just meet their standard.
Okay, how often should I test my grounds?
All right, now the main thing to avoid here, this is pretty much your call. and it has to do largely with the environment that you're in. So if you're in Florida, you want to probably want to do quite a bit of testing because they get so much lightning down there. And keep in mind that your electrode can do its job, and it can destruct underground in the process of fault clearance. So you may know that you had a lightning hit on your facility last night, but everything's running fine, and so you know your grounding system did its job and you're good. But in the process of doing that, especially if you have something like a grid, that can break apart underground. And you don't know that, visually, you don't really know that. So that's why you're testing your ground. And so if you're in a bad environment, you can set your own schedule. But the main thing to look out for, the way routine maintenance testing is typically done, the operator will decide, or the maintenance foreman or whatever, he'll decide, we'll test every 6 months, or we'll test every year during the annual shutdown or things like that. Well, for most electrical maintenance type testing, that's, kind of industry standard. But what you want to avoid in ground testing is don't do it on a regular basis where you fall into the same time every year. Select a number of months, like 7 months or 9 months or something like that, because that way you're going to fall around the calendar from one testing period to another. You're not always going to be testing at the same time of year, because depending on where you are, your grounding can vary quite a bit around the calendar. And especially if you're up where you get hard winters, the dead of winter can be really bad if you get frozen soil. And also August or a hot, dry summer can be really bad. So you want to make sure that you're testing at those times of year, because those are your worst case scenarios. The spring and the fall are generally fairly good, reasonably temperate and moist ground, and so you get pretty good test results. You do the same thing in a hot, dry August, your resistance is going to be much higher. So you want to set your maintenance schedule to deal with those parameters.
Okay. And how do I go about designing a good ground?
Okay. There's pretty much two ways to do this. Very commonly done is drive and test. You add a rod, you either drive deeper or you add parallel rods, and you run a test, and you're trying to get 5 ohms and you got 7.5. So, okay, we'll add another rod and we'll test it again. Now that's effective and it's very commonly done. The limitation of it is you can hit the law of diminishing returns, where, okay, the last time I added a rod, the resistance went down 10%. That's pretty good. When I add another rod, well, this time it only goes down 2%. So you can end up getting into a situation where you're driving and testing and you're getting smaller and smaller increments. And that can become counterproductive. It works a lot of times, but not always. So the alternative to this is to have a software program on your computer, and you can get these from the grounding materials companies. So go to them and inquire, and I think they will probably send them to you for no charge. I can't say that for sure because I can't speak for them. But I used to have one on my laptop, and we lost it in a changeover one time, but they work very well. They're simple software programs that you can install in your computer, and they'll ask you what you want to do. They'll basically ask you, what is the ground resistance that you want to meet? Do you want to do a deep driven rod, or do you want to do multiple parallel rods? And then the most important bit of data that you have to put in there is the resistivity of the soil at your site. And if you tell the software program those parameters, it may ask you a couple other fundamental questions, but if you put all that data in there, it will design the system for you. And it will show you that, well, you want to have 20 10-foot rods, and this is the configuration you want to arrange them and things like that. And then, you know, that's a very effective means, and you're good to go. Okay.
Okay. And how do I hook up my leads?
Okay. On this one, this is pretty much according to the procedure that you're going to be following. So what very often is done, I mentioned this before, the operator hooks up the leads, runs out the, hooks them up and runs them out the maximum distance and takes a reading. And yeah, if you're lucky, you may get a good reading, but you really don't want to do that. You want to hook up your leads and follow a test procedure. And there are a number of them, and they will tell you where your leads and your probes should go. And this is an example of what we're showing you right here is what you will commonly see in the literature is 62%. I can't go, you know, with the time limitations of this particular webinar, I can't go into detail on that, although I will certainly be glad to discuss it with anyone. But what it is, on a perfect system where there are no attendant problems, you will get a good reading at 62% of the distance to your current probe. And so this is a real quick test. It's a good way to get in and out of there on one measurement. The problem with it is, what happens if there's a water pipe or a live electrical line, utility line running underground right there where you put that rod to? Well, that's going to influence your reading. So there are a number of pitfalls to doing this. And so the main way of dealing with this is to follow a procedure. And the procedures, when you can read that little manual that we're going to send you, and you'll see these procedures in there, and you will see that they have built-in proofs written into them. And so they tell you how to hook up your leads and where to put your probe and how to run your procedure so that you'll get a good, reliable test result. And you can submit that to your client and they'll be happy with the result.
Okay. And how do I know how far to extend the leads?
Okay, again, that depends on, that's dependent on the test procedure that you're using. But what you will see in the literature very often are these tables. And the tables will tell you, take the maximum dimension of your test electrode, which would be the depth of a single rod, or would be the diagonal of a grid, for instance, and then use a multiplier. And so we see these typical multipliers. Now, you will see that in the literature quite frequently. And the main thing to be aware of is these are not scientific. These are the results that field operatives doing a lot of field work became familiar with and became recommendations. And the idea is that if you follow these directives, you stand a pretty good chance that you'll get a good reading on one test and you won't have to repeat. So it's a good idea to follow these tables if you can. But if you can't, it doesn't mean that you're out of business. It doesn't mean that you can't test. What it does mean, well, for instance, if you go ahead and you did a full of potential, for instance, in lesser constraints than what these tables would show you, and you get a good, reliable result, you get a horizontal line, your result is good. don't worry about it. You're good. So these are just recommendations. They're not scientific demands, but they do give you a reasonably good chance of getting a reliable result on one test and not having to repeat.
Awesome. Okay, what is the significance, Jeff, of the provided lead lengths?
All right. The thing to avoid here is with our testers particular, and probably a lot of other models that you'll get, the leads are cut to that 62% rule. So if you ran them out to their maximum distances and took a measurement, there's a fairly good chance that you would actually get a good reliable result. But the thing is, you want to avoid just doing that automatically. That's what a lot of people do. And they very well may have a good reliable result, but without submitting it to some sort of proof, like graphing a fall of potential graph, for instance, or in the case of some of the other test methods, there's mathematics built into them that will prove your answer for you. But if you don't do that, there is a chance that you may not have a good result and you're walking away with that. So if you then, on the other hand, if you do employ a proof and the proof tells you, well, your current probe wasn't out far enough, the resistance, and the big problem there is that the resistance that's associated with the current probe gets into your measurement because the current probe is too close. And so that skews your measurement and puts an inaccuracy into that. So what you have to do in those situations is get the current probe further away. And so you can do this by adding more distance onto your potential and current probes and getting them farther apart. And the main thing we have in our catalog, for instance, you can buy these additional reels, and you can run that current probe out from here to China, so to speak. There is so much resistance tolerance in the tester that you aren't going to put enough wire on that tester to load it down by the resistance of the wire. Where you do run into a problem is the resistance of the probe. And so that, fortunately, modern testers, the old-time testers, the operator a lot of times had to deal with that. But with the modern testers, they tell you. So don't worry, the tester will pop up and it will tell you you got too much resistance on your probe. And in that case, just go out there and stamp it down and put water on it, and just, get the indicator to show you thumbs up or a check mark or whatever, and you're good. So you can add a lot of wire onto your setup, and eventually you'll get enough distance to have a good reading.
Okay, and does it matter how deep I drive the probes?
Okay, again, another common question that more or less goes back to the old testers, where the older testers, the operator had to, he had to make a judgment because they didn't necessarily tell you that your probe wasn't deep enough, and so they used to, bang in pretty deep probes and all. And there's still a lot of that being done, so keep that in mind. But with the modern testers, they just tell you there's too much resistance on your current probe. Okay, you go out there and you water it or whatever. So on the modern testers, it's pretty much in typical environments, you just hand push them in. Because remember, if you're going to hammer in deep probes, well, you got to get them back out again, and that could be hard on your back. So fortunately, in most situations anymore, you don't have to do that. You can usually just hand push them in. So just be familiar with the indicators on your tester that will come up and tell you whether your current probe and your potential probe are in deep enough where they have too much resistance around them. But those circuits on good modern testers will tolerate thousands of ohms of resistance. So it generally isn't really a problem. So don't overdo it. And then, you have an issue with your back and your knees trying to get the probe back out again. But there are extreme examples where you may still need to do that out in a desert or something like that, but not in most environments.
Okay, and so what about my testing is all on concrete and macadam. How can I drive the probes?
Yeah, in the old days, that again was a problem that sometimes defeated testing, but not anymore. Let's say you're doing parking lot lighting, that can be a problem. Airport lighting, another example. But no, with modern testers, all you have to do is just read the specs of the tester. You should be able to, if you have a reasonably good modern tester. Doesn't necessarily have to be ours because there are competitive testers that give you the capability. So just make sure that you can do that. But you can run surface testing. And what you're doing is instead of driving a probe in, you're laying it on the surface. So a good thing to use in this case, sometimes the actual stiff rod probe sometimes will work, but it's much better to have something like a coiled metal chain or a metallized grounding mat that are flexible and they'll mate well with the underlying surface. And then you pour water on them so you have an electrically conductive path into the surface underneath. And you just use those in place of driven rods. And you look at your display, and as long as the display doesn't tell you that you have too much resistance, then you're good. And if the display does tell you that you have too much resistance, then just add more metal. So if you're using a metal chain, just, use a longer chain or add some extra links onto it and try it again until your indicators tell you that you're good to go. And then using that for a probe instead of driving into the soil, it will work just as well on something like a parking lot surface, for instance. And you can go ahead and get a perfectly good, acceptable test.
Okay. And let's see, if I water the test probes to improve contact, won't this influence my results?
Excellent question, because it does seem to be to the point. But actually, you're fortunate. The answer to it is no. You're not measuring the resistance of the test probes. The tester knows what that is. It takes it into consideration when it's calculating your test result. So you can pour all the water in the world onto those probes, and it will help you get a good test, but it will not influence the result. If you pour water on your test ground, then yeah, you're certainly going to influence your result. So, not to be funny or anything, but if you want to fool the inspector, before he gets there, you can water your test ground. It will certainly lower the resistance. And in a more practical sense, just the general performance of your grounding system around the calendar on rainy days, that resistance goes down quite a bit. And so water does influence the test ground, but it does not influence your measurement. It makes the probes more effective, but it does not influence your measurement.
Okay. I have no room to stretch out my leads. What do I do?
All right, in that case, that's where you come into what we've already mentioned, the dead earth method. Again, I reiterate, you're dealing with a third party. This is described in IEEE 81. So you can do it. It's a drop dead method. It's where you would use this only where you can't do anything else. But yes, in that situation, you do a 2-point test and you run it to some sort of a return, a metallic low resistance return, which would be something like the water pipe system or possibly building steel. There are limitations to it. The limitations are mentioned in IEEE. You do want to be familiar with them if you're dealing with, especially if you're dealing with a third party. You want to know what those limitations are so that you can talk effectively with questions from a third party. But you can do this. So just make sure that your situation is such that you can't do any other method. This is the only thing that remains to you. And do your test and submit your report within the parameters that are the given limitations of it in IEEE 81.
Okay. What safety precautions should I observe when performing a ground test?
Okay, I think we have a little slide here, I think, coming up mentioning what a PPG or whatever, personal protective gear or whatever. You see that coming up in the literature frequently. You want to use basic protective equipment, particularly what you're wearing, gloves, boots, and also you can work on a grounding mat. The tester itself does not have enough power to injure you. A ground tester needs very little voltage and very little current to operate. And so the tester itself is not dangerous. However, the test item, which would be now, if you're on an isolated ground somewhere on a construction site that hasn't been energized, you really have very little to worry about. But on the other hand, if you're testing to an energized site or something that's actually connected to the utility, your problem there would be if an event occurs on the line somewhere. There's a lightning strike 2 miles away or something like that, and there's fault clearance going on, and yeah, you're connected to the ground and you can be part of that path. But two things: use basic industry standard protective gear and protective procedures. Your basic industry standards, and then also for the site that you're on, check what their particular safety procedures are, and just make sure that you stay in conformance. And you really don't have any kind of a risk that you really need to be concerned about.
Awesome. Okay, I need greater lead lengths than what your kit provides. What should I do?
All right. In that case, here we are. We have these additional reels that you can very conveniently string together. And if you have a tester that is not made by us, that does not mean that you had to go somewhere else. You can use these just as well. It's just wire. There's not a lot of demand on the wire that you use to perform a ground test because the current is very limited. The voltage is very limited. So there's not a lot of demand on the wire. 14 gauge is perfect. You don't need to go necessarily beyond this. You can use scrap wire at your facility. You don't necessarily have to buy specialized wire. The main thing to keep in mind, again, know your tester, know what the symbols are on the display. And this can be somebody else's tester. It works just as well. There should be symbols on the display that will pop up and will tell you if there's a problem, and we'll pretty much tell you how to deal with it. So you can add all the wire that you want You can buy additional reels, and you can, like I said, you can also use scrap wire. There's really nothing demanding about this. So don't be dismayed if you happen to run the wire out to its maximum length that came with the tester, and you end up getting a flag on your display that says too much resistance. Don't be dismayed by that. It's very easy. This will never defeat your test.
Awesome. Okay, the next question is one that actually people are asking right now in the chat. It has just rained heavily. Will this influence my test?
Okay, yeah, we did kind of touch on this a little bit. It is important, but the main thing to keep in mind, if you're doing routine maintenance testing, you just want to make sure it's okay to test when it rained heavily. Just be aware that the reading that you're seeing there is a bit deceptive. It's going to make the picture look a little bit more rosy than it really is. So just make sure that you test around the calendar, or if you're just doing, if you were just commissioned to do a one-time test and then you're not going to stay on that property, then it's a good idea to tell your client, this isn't the best day to do that. Maybe I better wait till next week or something and come back and perform the test again. Once the rainwater drains away, you won't get such a rosy picture, but it will be more realistic. So you do definitely want to take that into account and work it out with your client. Okay.
Okay, and the last question is, I have a ground installed in sandy or rocky soil. What can I do to test this?
Well, the testing, yeah, that comes up all the time, and the testing itself isn't particularly different. You're still going to do fall of potential, or if use some other method, if you want to do slope method or whatever. And don't be dismayed by me mentioning these methods in the booklet that Meredith is going to send to you. They're all described in there, so you'll know what they are. But you just go ahead and do the method that you intended to do. You're not defeated in the method itself by these types of soil. But where you do run into a problem is you're going to need more, but basically what it comes down to is you're going to need more wire. So if you're in sandy or rocky soil, yes, they are very hard environments to get a good ground. And it's going to be tougher to meet your 5 ohms or whatever you're testing to. And so, yes, you may need to add more rods, or you may need to do something like that. But as far as the test itself is concerned, the main thing that you're going to run into is that you may need to go a lot further out to get a reliable test result. And so just be prepared with more wire is pretty much what it comes down to. And if you're working against a contract with a client, make sure that you advise them that this may take you more time than it does in more favorable environments. So a lot of times there may you may have some kind of a contract with a company that is all over the country or is in a large section of the Southeast or whatever, and so they may be used to seeing relatively quick tests in the good grounding environments, and then just make sure that they're aware. Now you're going up into the foothills of the Appalachians or something. This is going to take you a bit more time. So just make sure that your client knows this, and you don't, get into a lot of argumentation because this took you twice the time that it did on the last test that was done 100 miles away. So, just work that into your test procedures and you'll be fine.
Awesome. Well, thank you so much, Jeff. If you guys want a free copy of Getting Down to Earth, our guide to ground testing, please visit us.megger.com/promotion/vf/getbook. I will also send you this link via email, and then just use offer code FAQ_webinar, and you'll select Getting Down to Earth as the booklet you want. And coming soon, we will have another webinar just like this one, technical answers to common questions, but part 3 with instrumentation. So be on the lookout for that. That will be about ground testing too. And thank you all so much for coming. Thank you, Jeff, for presenting. And we'll see you soon.
And I'm here to entertain questions. No problem.
I forgot to mention again, yes, if you asked a question in the chat, Jeff will get back to you via email. So be on the lookout for that. Thanks, everyone. Bye.